Sounds good.
Good evening, everyone, and thanks for your interest in tonight's event. Also, thanks to Park for their continued support of our series. I'm Greg Diegues, one of the co-founders of the Energy and Clean Tech series at the MIT Club of Northern California. I'm pleased to be able to introduce to you tonight two important people. The first will be Dr. Kerry Emanuel, about whom you've heard very much, or he wouldn't be here. The second person's a surprise, whom I'll introduce to say a few words after the Q&A with Dr. Emanuel. And after he finishes his speech, he's going to address, we have 2 pages of questions submitted by people who registered. He's going to pick some of those that he might not have covered during his talk. And then after he addresses a handful of those questions, we'll open the mics to the audience and pass them around, and you can ask additional questions. When we began the Energy and Clean Tech series over 10 years ago, there were multiple reasons to pursue clean technology. It seemed evident: energy independence and national security, financial health, and pollution reduction. Now, while we held a few early events on climate change and water, we basically focused on new technologies, and we got a lot of interest in jobs and investments surrounding those technologies. We had a good audience. We spun off some of the members of our group to found the Clean Tech Open, which some of you have heard of, and I hope it fostered a growing interest in the issues. However, looking back over the last 10 years, it's surprising how little has been accomplished in the area of clean technology as a percentage of our national energy. And there has been a surprising debate about the impacts of human pollution in the air, in the ocean, and on the climate in general. Thus, we feel it's timely to revisit one of those driving forces behind clean technology, specifically the issues related to pollution. So tonight we're kicking off a series of climate change events, which will begin with tonight's overview of the issue, and then delve into atmospheric and oceanic impacts, and finally explore the economic and policy issues surrounding all of these. These sessions will be interspersed with our normal events over the next couple of years. Now, during those last 10 years, in this conflict-strewn wasteland of climate change debate and doubt, there ventured one of that rarest of species, a Republican climate scientist with an open mind. So for our kickoff event, we're pleased to have with us Dr. Kerry Emanuel, the award-winning meteorologist and climate scientist and professor of atmospheric science at MIT. Many of us do not have the time or expertise to follow these issues fully, so we welcome the opportunity to have Kerry inform us about the current situation. Kerry?
Thanks, Greg. Okay, well, we're getting set up. Can you all hear me? I just wanted to start off by saying that I'm really delighted to be with you here tonight, and it's also particularly nice to see so many old friends in the audience, and it's really nice for me to do that. I'm going to talk to you, as Greg said in his very nice introduction, about the problem of global warming tonight, but I want to preface my remarks by saying that there's something that gets lost because this is such an important debate, and that is how exciting as a pure science climate science really is. It's intellectually really neat stuff. Okay, it's not, if there were no such thing as global warming, it would still be a really, really fascinating field. And I'm afraid that that gets lost in all of this. That's why I'm in it. That's why most of my colleagues are in it. And we would be doing this if there were no such thing as global warming. But I promised to talk about global warming, so that's what I'll talk about. I flashed up here that, of course, I'm at MIT, but a colleague of mine, Dan Rothman, and I started a climate science think tank called the Lorenz Center, which is being supported by an endowment raised by MIT's School of Science to go back to basics and really get some of the world's top young physicists, biologists, chemists, and so forth interested in this problem. So what I'm going to try to do with you this evening is, first of all, as promised, to give you something of an overview of the problem, where we are with it. and to talk a little bit about solutions, which is not really my expertise, but I do end up speaking to a lot of people whose expertise it is, and it's something we have to touch on when we talk about this problem. And I'm going to summarize right at the beginning of my talk what I think the essential points should be on this. And the first is that our climate over geological time scales is not particularly stable. And I'm going to show you some examples of that. Climate science is not a new science. I think a lot of people think it is. It's actually got a very long and illustrious history. Human activities can and demonstrably do have a strong effect on climate. I hope that you will be persuaded of that. The idea that we're altering climate is based on a whole lot more than complicated climate models. I'm actually a fairly strong critic of complicated climate models. I like simple models. I do see the need for them, but it's a mistake to think that what we know about this problem is based mostly on this particular tool. Another point, which has been very strongly quantified in recent years, is that the idea that we are changing climate is not very controversial amongst people who actually study climate. I don't mean retired physicists and all sorts of people who advertise themselves as climate scientists. I mean real climate scientists who spend their careers working on this problem. So let's begin with the first point. Earth's climate isn't terribly stable. Well, I'm sure you know this already. This is a map of what North America might have looked like from space 20,000 years ago at the peak of the last glaciation, which was one of approximately 10 that have occurred over the last 3 million years or so, when we had ice covering, well, where I live, Boston was under about 1.5 miles of ice. So that's a lot of climate change, okay? These ice sheets come and go, and I'm going to show you a little bit later on the talk that one of the remarkable achievements of my field in the last 100 years, actually, is identifying pretty much why this happens. This is no longer a complete mystery. And if you don't already know the answer, I'll be talking about that. As that last ice age ended, this is what happened to sea level. So this is time. This is 24,000 years ago. This is today. This is sea level relative to today. This is in meters. So at the peak of the last glaciation, sea level was about 140 meters lower than today. It's about 400 feet. So most of the people in this audience have been at MIT, and if you could have crawled out from under that giant ice sheet, you could have easily walked to Provincetown without getting your feet wet. Sea level, there was basically no water. And it's a huge change. And look at the last 7,000 years here. It's been remarkably stable. On geological timescales, we've been very fortunate to live in this last 7,000 years as a civilization during a time of remarkable climate stability called the Holocene. Okay? It is not a coincidence, we think, that civilization developed largely when the climate stabilized. Of course, humans as a species have been around for much longer than that. Now, I'll come back and talk about this later, but here's some numbers for you just to sort of try to put in your head. The polar radiative forcing variations that led to this were on the order of 10 watts per meter squared, which you might compare to the radiative forcing that will happen if we double CO2 of about 4 watts per meter squared, okay? Just remember those numbers if you can. And the global mean temperature that was associated with these fluctuations was about 5 degrees centigrade. Of course, it was much more than that in the Arctic, but the global mean was the fluctuation was about 5 degrees. But here's a record. One of the really fantastic achievements in climate science in the last few decades has been understanding what's happened over the last, especially 1 million years or so, through the analysis of ice cores and deep sea sediments. It's fantastic, really, and it's a story that I could spend a long time telling you about, and I think you'd find it very interesting if you don't know it already. Here's a chart this one goes back 450,000 years, and is based on some different ice cores. And what you see here is basically a proxy for temperature at 2 different places, and then a really accurate proxy for the total volume of ice on land on the planet. Remarkably, that's that can be determined just by analyzing the ratio of two isotopes of oxygen in deep sea, in the shells of microorganisms buried in the deep sea. If you know what the delta O18 of seawater is, you pretty much know what land ice is. And you can see that these co-vary, and that we're currently in one of these interglacial periods where it's relatively warm. Over much longer periods of time, the Earth has varied in even more spectacular ways. So one of the things that has been discovered in just the last few decades, although it had been hypothesized before that, is that roughly 650 million years ago, the Earth went through some cycles that were really spectacular, ranging from an entirely ice-covered planet, or very nearly ice-covered planet, which we call a snowball. And the problem for us was once you got into that state, how would you ever get out of it? Because you're basically reflecting all the sunlight back to space, right, once you're in that state. And it's very interesting how we got out of that. When we did get out of it, it happened very spectacularly, and we went all the way to states where there was no ice anywhere on the planet, including at the poles. Okay, so places like the north of Greenland might have looked like what you see in this picture at the bottom here. So we rapidly varied between rather extreme states. This sort of conveys in a very encapsulated way the fact that the Earth's climate has varied terrifically on all kinds of different timescales and for different reasons. It's not all the single cause. Climate science, human timescales, has got a fairly long and illustrious history, and we can talk about two individuals to start with. Jean-Baptiste Fourier. I bet some of you remember learning about Fourier series when you took math courses, right? Some of you probably even use them today. Well, here's the guy. He's a gifted French polymath. And he is credited in my field for being the first to understand that there was such a thing as a greenhouse effect, that the atmosphere trapped infrared radiation. Now, this fellow, this dour-looking Irishman, John Tyndall, was the physicist who really started to quantitatively understand what the greenhouse effect does and what it's based on. And we'll come back in a minute and talk about him. Here's a picture of the apparatus he built and used to measure the transmission of infrared radiation through the air. In the early part of the 20th century, this man, who was a mathematician, Milankovitch, took up a hypothesis that had been proposed some decades earlier, but really put some meat on it. And that is that the glacial cycles I just alluded to, the sort of 100,000-year glacial cycles, were being forced by wobbles of the Earth around the Earth's rotation axis and variations in the orbit. And there are three principal ones, which are perfectly periodic, almost perfectly periodic, that we'll be concerned with. You know that the Earth's orbit around the sun is eccentric, but the degree of eccentricity wobbles thanks to the influence of other planets, largely, with a period of about 100,000 years. The tilt of the Earth's axis, currently 23.5 degrees, also wobbles. That's called the obliquity. And it has that particular wobble has a period of about 41,000 years. And then the equinoxes precess, that is, the axis of the Earth's rotation precesses like a top. And because of the ellipticity of the orbit, that affects the distribution of sunlight between the two hemispheres. So right now, in this cycle, the Earth is actually closer to the sun in northern hemisphere winter, okay, and further away from. And the reason there are seasons, of course, is because of this tilt, not because of the distance of the Earth from the sun, but that does affect the seasonality. Right now, it's actually modifying or moderating the seasonality. When we're in the other, 10,000 years from now, it will be making the seasons more extreme. And nobody believed him at the time, but these ice core records have basically been used to prove Milankovitch right about the basic cause. Now, how do we know that? Well, here's an example of how we know that. Here's a two-time series going back 1 million years. So the numbers here are in thousands of years. So that's 1,000, 1,000, or 1 million. And you see two time series on here that are completely different measurements. The red curve actually is not a measurement. It's prediction from Milankovitch's very careful orbital mechanics, just physics 801, but writ large. This is the this is the amount of sunlight received by the Earth north of 60 degrees north over the course of a year. And of course, that's received in the summertime. And the fact that it oscillates is because of these orbital oscillations. The black curve is the time rate of change of the ratio of these two isotopes of oxygen in deep sea sediments from the shells of microorganisms. Really quite a different thing altogether, which you might remember me saying is a very good proxy, an excellent proxy for the amount of land ice. So this black curve can be interpreted as the rate of change of continental ice sheets. And you can see how well correlated these are. They're not perfectly correlated, but it really is true that ultimately these ice ages are caused by variations in the Earth's orbit around the sun. Now, there's some complexity in exactly how the climate responds to that. So the equatorial climate responds a lot more than the orbital mechanics would predict. And that's now thought to be because indirectly, these oscillations cause the carbon dioxide content of the atmosphere also to vary. It's being forced, in this case, indirectly by these these orbital variations, but that has a feedback on tropical climate. Another very important person in the history of climate scientists is this, what is it about climate scientists? They look so unhappy, right? I don't get this. Anyway, this is Svante Arrhenius, who's a brilliant Swedish chemist, apparently a rather nasty individual, but he accomplished a lot scientifically in his lifetime. And we'll come back and talk about his contribution in a minute, too. Going forward into the 20th century, the Englishman, Guy Stewart Callendar, was very worried about the fact that, or he believed that the carbon dioxide content of the atmosphere should be going up, but they didn't have good measurements back then to show that. And in more recent times, the first report to the US National Academy of Sciences, written by my thesis advisor at MIT, Jewel Charney, and co-authors in 1979. And what they concluded, based on very simple models mostly, is that when you double the CO2 content in the atmosphere, you're going to raise the global surface temperature somewhere in the range of 2 to 3.5 degrees C, with greater increases at higher latitudes. Now, here comes the part which is perhaps the most counterintuitive and causes a lot of people problems, including it caused me a lot of problems early on in my career, is why is it that human activities, which on the scale of the Earth still seem pretty puny, can have a strong effect on climate? And this is actually something that was discovered arguably by John Tyndall at the end of the 19th century, using this, here he is again, the Irish physicist, using this apparatus to measure the transmittance of infrared radiation, which is the band, broadly speaking, that the Earth at its temperature radiates upward to space, how that radiation passes through the atmosphere. So he came up with some really, really surprising results. I still look at these results and I'm kind of shocked by them. This is more than 100 years ago. Well, you know that our atmosphere, about 99% of it, is made up of oxygen, nitrogen, and argon. There's a little bit of argon there. And his discovery was the molecular oxygen and molecular nitrogen are almost completely transparent infrared radiation and solar radiation. It's not exactly true, but it's to a very good approximation true that both sunlight and infrared radiation just go right through these constituents. And that the fact that, nevertheless, a great deal of infrared radiation and some solar radiation is absorbed by the atmosphere were thanks to a handful of trace gases, the most important of which is water vapor, H2O, but also carbon dioxide, nitrous oxide, and some others. And together, remarkably, they make the lower part of our atmosphere almost opaque to infrared radiation. Almost opaque. There's a lot of trapping. And nevertheless, still largely transparent to solar radiation. The other, he didn't talk about this, but we of course, he recognized, and it's fairly obvious, that clouds, that is condensed water, also have strong effects both on solar radiation, which we know all about in Boston, the effect of clouds on solar radiation. I don't know about if you know it out here, but we know it, but also infrared radiation. These trace gases make the difference, and this was recognized 100 years ago, this is not new and it's not based on computer models, between a planet that we can inhabit, whose current mean surface temperature is about 60 degrees Fahrenheit, and one which we could not, whose surface temperature would average 0 degrees Fahrenheit, that handful of trace gases. It was a pretty extraordinary discovery. Let's try to put that in graphical form. Here's nitrogen. Here's oxygen, right? 78%, 20.81%. There's argon, which is also transparent pretty much to radiation. And the greenhouse gases are that orange sliver. You in the back of the room, can you see that orange sliver? No. Okay, you're not supposed to be able to, but it is there. It's there. Those are the greenhouse gases. Right? There's not much of them. It's actually a far worse situation even than you see on this graph. So that orange sliver is what makes the difference between 0 degrees Fahrenheit and 60 degrees Fahrenheit. We depend on that orange sliver, okay? And this is not new science, and it's not controversial science. It's absolutely rock solid, okay? There's been no controversy about that for a long, long time. It's worse than that because the most important greenhouse gas, water vapor, which is about 1/4% of the mass of the atmosphere, but it has a lifetime in the atmosphere of 2 weeks. In other words, if I put water molecules artificially in the atmosphere, 2 weeks later they're back in the ocean or in the ground or something. They cycle through the atmosphere, and the control of the water content through the Clausius-Clapeyron equation is mostly by temperature. Not exclusively, but mostly. So it's a feedback for climate. If you raise the temperature, you'll have more water vapor. Water vapor is an important greenhouse gas. What I haven't told you here, because I decided not to do the usual Physics 101 tutorial, my mother said you shouldn't do physics tutorials after dinner, so I'm trying to adhere to that. It's actually not complicated to understand that the atmosphere is absorbing infrared radiation leaving the Earth, and it's re-radiating that infrared energy both up and down. So if you sit at some point on the Earth's surface and you measure sunlight coming down and you measure infrared radiation coming down from the atmosphere and from clouds, remarkably, over the course of a year, on average over the world, we get more than twice as much energy, actually almost 3 times as much energy from the atmosphere and from the clouds as directly from the sun. That's how powerful the greenhouse effect is. That's why it makes a difference between 0 degrees Fahrenheit and 60 degrees Fahrenheit. But the most important gas is controlled by temperature, leaving the actual control along time scale to carbon dioxide, methane, ozone, and a few other gases that you couldn't even see in the front row if I put them on that pie chart, okay? It's really kind of an interesting situation. So climate is strongly influenced by the so-called long-lived greenhouse gases. One of the most long-lived is carbon dioxide. It has a residence time of between hundreds and thousands of years in the atmosphere. And these together comprise 0.04% of the mass of the atmosphere. So we're utterly dependent on gases that are a tiny, tiny fraction of the total. The concentration of this most important gas has increased by 43% since the dawn of the Industrial Revolution, and it's on a track to double in the lifetimes of many people in this room. Now, this was recognized by our dour-looking Swedish friend, Svan Arrhenius. I want to come back to him. He was the first scientist that we know about who started to worry. By then, of course, the greenhouse effect was pretty well understood quantitatively. He was worried about what would happen because he recognized that industrial activity was proceeding apace. He started to worry about what would happen if we started to change the greenhouse gas content. And he made measurements of the transmissivity of CO2 based on some of his colleagues' measurements of moonlight, actually. They really had interesting ways of doing science. And with nothing more than a paper and a pencil, what more was there in the end of the 19th century, came to this conclusion. Any doubling of the percentage of carbon dioxide in the air would raise the temperature of the Earth's surface by 4 degrees, okay? And if the carbon dioxide were increased fourfold, the temperature would rise by 8. So he this is 4 degrees centigrade, by the way. I should have put that down here. 4 degrees centigrade and 8 degrees centigrade. He recognized that the increase would be pretty much logarithmic, which we all recognize to be true today. And if you look at the latest report released by the Intergovernmental Panel on Climate Change last fall, they reckon that doubling CO2 would change the surface temperature between 1.5 and 4.5 degrees. So Svante Arrhenius' estimate with a pencil and paper was within that range of uncertainty. So the only thing that's really changed in the intervening almost 100 years, or more than 100 years, is that the error bars have gotten bigger, okay? So I would say that the prediction made by Arrhenius has pretty much been verified. So here is a chart going back to 1880 of the natural logarithm of the CO2 content in blue and the global mean surface temperature in green, okay? And yes, there are all kinds of variabilities in temperature, some of which are natural, some of which are forced by other things besides CO2. There's a lot of sort of chaotic climate variability on short time scales. There's this sort of rapid rise in the early 20th century, and then actually a decline or leveling off in mid-century for a few decades and a rapid rise. This is CO2. His prediction wasn't too bad, okay, for somebody operating with a pencil and paper. Now, I want to try to convey to you the next and penultimate point amongst those I'm going to show on this series of slides, is this notion that we are basing conclusions about what might happen to the planet exclusively on hopelessly complicated models, all right? Well, climate models are pretty hopelessly complicated. They're some of the most complex software codes that have been written, at least in the scientific domain, for a long time. Millions of lines of code. We could talk about climate models if you want, but what I want to try to say to you first is that what we think we understand about climate, and there's an awful lot we don't understand, we shouldn't kid ourselves about it, comes from a lot more than climate models. So I've already shown you one of the other ways we know something about climate, which is through this amazing and very successful endeavor called paleoclimate. It's a branch of geology which tries to find proxies for climate variables like temperature and rainfall in the geological record. What do we know from that? Well, here's a chart showing the carbon dioxide content of the atmosphere going back to just before 1750. And I want to tell you where this graph comes from. These red dots are from direct measurements that started in 1958 in Mauna Loa, Hawaii, by David Keeling, of just direct measurements of carbon dioxide. Now, if you're away from industrial sources, as you would be in Hawaii, these are pretty well mixed greenhouse gases. They're going to be the same there as in Antarctica because of their long lifetime. And you can see it going up here. The blue dots come from analyzing bubbles of atmosphere trapped in ice cores. So when snow falls, it traps bubbles of air. Subsequently, they get frozen in place. You can analyze that in ice cores, and you can see how nicely congruent they are. So the pre-industrial level of carbon dioxide is thought to be close to 280 parts per million, and it's been going up faster and faster. And this chart stops early in the last decade. Last year, it passed 400. Okay, so we're past 400 now. We're off this chart, and we're sailing upward. Let's try to put that in deeper historical or deeper geological context. This is now data. The black, again, are from Mauna Loa. This is ice core data going now back to 900 AD. So you can see that before the Industrial Revolution, the carbon dioxide content was pretty stable. And this is going back to the peak of the last ice age. So this, as the ice retreated, carbon dioxide actually rose from about 180 parts per million to gradually up to 280. And this has to do with the natural biogeochemical cycles of the planet, which are not terribly well understood. The CO2 went up mostly as a consequence of the fact that it was getting warmer from this orbital forcing, but also as a feedback to that. was fairly stable. And that spike at the end, which is now up off the top of this graph, is what we've done. Okay? There's no controversy about that, by the way. There's nobody who works on these things has any doubt that this is what we did. This is the same thing, but for methane, which is another fairly important greenhouse gas, and you can see the recovery from the ice age and then this big spike. We can also use paleo techniques to try to understand temperature of the planet, or of localities at least, on various time scales. So this is a chart going from 0 AD to more or less the present, and it shows different reconstructions of temperature by different groups using different proxies, things like tree rings and corals. And by comparing these curves, you see some measure of uncertainty in this. As you go back in time, naturally, the uncertainty increases. This black curve is what we've measured since we had enough thermometers around the world to measure it. This is the global mean temperature in 2004. So there are natural variations, no doubt about it. And what's unusual about the record is the extraordinary rate of increase at the end, coinciding with the Industrial Revolution. That's sometimes been referred to a hockey stick. It's more like a bent hockey stick of the kind you might see after a Boston Bruins game, right? So here is a temperature record from the Arctic, not global, based upon oxygen isotopes, tree rings, and other proxies going back again to about 2,000 years, showing some uncertainty, but a general decline of temperature until the Industrial Revolution and a fairly rapid rise after that. And besides the proxies, we have the instrumental record. So here is, as you go back in time, there are fewer and fewer thermometers around the world. The uncertainty gets bigger. This is just an analysis of global mean temperature by various different groups around the world, including the one here at Berkeley, this black curve with the shading in the diagram. And they converge a lot because we've had very good measurements around the world since the middle of the 20th century anyway. So we have interesting variability, and then we have this fairly rapid rise in the last 40 years or so. Since about the late 1970s, we've often been able to say something about atmospheric temperature based on observations from space of infrared radiance and other properties. Here compares direct estimates based on thermometers in blue with two different techniques for inferring temperature from satellites in green and red. And you can see that chaotic variability whenever you start looking on timescales of years or even decades. There's an awful lot of this that goes on, but a general upward trend continuing. Global temperature change isn't globally uniform. There's no reason why it has to be. It's not. There's all kinds of good reasons why it's not. This is just the linear change in surface temperature from 1901 to 2005. And you can see that most of the warming, where you see the reds here, is, first of all, continental. The seas are also warming, but not as fast as the land. There's very good, fairly straightforward thermodynamic reasons for that. But there's a lot of variability. The southeastern US has been cooling, as has the far North Atlantic. This is an estimate of the heat content of the global oceans down to 2,000 meters, roughly half the world's oceans. Why 2,000 meters? Well, below 2,000 meters, measurements get problematic. This only goes back to the 1960s, but it gets better with time. The data get more plentiful. And we've had these wonderful robotic floats that go up and down in the ocean for the last decade or so, called Argo floats, which are doing a much better job measuring temperature in the ocean. That's the red. And you can see this upward trend in the heat content of the ocean. And if you compare that to the heat content of everything else on the planet, so the blue is the ocean, the red is the land surface itself, the atmosphere and land ice. And it's heat content, it's not temperature, it's the actual integrated heat content. It's the density times heat capacity times temperature. This simply makes the point, which is fairly elementary, that when you change the climate over these timescales, almost all of the change in the actual energy content of the planet is in the oceans, not the atmosphere, simply because the oceans are much, much more massive water is about 1,000 times denser than air and has 4 times the specific heat capacity. So it's the oceans where you really want to measure climate change, not the atmosphere. But we're more concerned, for obvious reasons, with what's going on in the atmosphere. Until very recently, the atmosphere was much better measured, on the other hand, than the oceans. How do we know that this recent increase in temperature is because of carbon dioxide? All we know is, well, carbon dioxide started rocketing up and temperature started rocketing up. Could be a coincidence. But elementary physics, not computer models, tells us that's what we should expect. But what kind of measurements can we bring to bear to point the finger at the actual cause? Well, here's one thing. This, once again, is global temperature trends over a shorter period of time, 1979 to 2012, based strictly on satellite measurements. So where you see the deep blues and reds, you're getting rapid warming and so forth. That's the surface. Well, it's actually the troposphere. It's the atmosphere near the surface. What I'm going to show you next is the same satellite looking at different channels in the infrared where the radiation is coming mostly from the upper part of the stratosphere. And that's the trend over the same period of time. Not quite the same period of time, 1979 to 2006. It's cooling. The upper stratosphere has been cooling dramatically. And that's exactly what basic physics theory tells you should happen with carbon dioxide. And it's interesting physics. Basically, what's absorbing energy on that level of the stratosphere is ozone. But what's emitting energy to space is carbon dioxide. There's hardly any water up there, by the way. So if you increase the concentration of the emitter, carbon dioxide, you increase the emissions and cool the planet. Now, if, for example, the sun or cosmic rays or something else had been warming the planet during this time, if anything, the stratosphere would be getting warmer, not colder. So this is almost unique fingerprint of increasing the long-lived greenhouse gases. But there's more evidence than that. Mountain glaciers, wherever you see red, since 1970 have been in retreat. Where you see blue, they're advancing. So most of the places, glaciers are retreating. Mountain glaciers are retreating. This is going to touch on a criticism of climate models. This is a series of both hindcasts and forward predictions by a large suite of global climate models of the areal extent of Arctic sea ice in the summer. Okay? Arctic sea ice covers most of the Arctic Ocean in winter. It retreats a little bit in the summer. This is September Arctic sea ice. The two different curves are for two different emission scenarios going forward toward the end of the century. The black is what's actually happened. Okay, so Arctic sea ice has been disappearing at a rate that goes far beyond the envelope of what models predicted. Okay, and we don't know why. It's been happening for quite a long time. Here is my own work on hurricanes. This is a measure of power dissipated by Atlantic hurricanes. The Atlantic is only about 10% of the world's total hurricanes, but we have much better measurements in the Atlantic than elsewhere. This goes all the way back to 1870. The green is hurricane power. The blue is the ocean temperature in the Atlantic where hurricanes form during the summer. And you can see a nice correspondence, except during this period, from 1939 to 1945, when that relationship temporarily collapsed. And I'll let you chew on that as what was going on during that time and what that might have had to do with this record. Theory suggested that I developed, suggested that due to global warming, we should see this change. All right, that red curve. So clearly the changes, whatever is causing them, are going way beyond what at least fairly primitive theory told us to expect. Another problem that isn't talked about nearly enough is not a climate problem. It's a direct chemical problem, a chemical consequence of just putting a lot of CO2 in the atmosphere. Half of what we're putting in, roughly speaking, gets dissolved in the ocean. So the dissolved CO2 content of the ocean has been going up, and so the pH of ocean water has been falling. And this is showing the rate of fall. In other words, the oceans are becoming more acidic. And this is particularly true in the North Atlantic, but basically all over the world, you see drops in the pH of ocean water. This is measured. Okay, the Southern Ocean has got a lot of drops. And this is a big concern for marine biologists who notice from laboratory experiments that corals and other microorganisms that basically build calcium or calcite shells, if you start increasing the acidity or the dissolved CO2 content of the water too much, they start to have trouble, okay? And a lot of these ecologists, and I'm not one obviously, think we're getting very close to the point where we're going to start really stressing these. And of course, I don't need to tell you what this would mean for the whole ecology of the ocean. Now, I build simple models that are really simple physics, like one-dimensional column models that Svan Harenius couldn't run, but Jule Charney and his team in the 1970s could easily do. And today you can run models like I'm going to show you the results of on your laptop, whatever that is, quite quickly. And when you do that, and you do experiments doubling carbon dioxide, this is just number of doublings, so this is a log scale down here. This is surface temperature in degrees C. Just a handful of experiments, you get about 3 degrees per doubling, which is right in the middle of the range produced by supercomputer models where you have to call the power company before you can turn them on, and you have to wait weeks or months for the output. So there are simple ways to do this. This is pretty straightforward physics. Here is a perfectly sociological point, but I have to make it, all right? Lots and lots of polls among people who actually do climate science. I don't mean, well, I went through the spiel before, people who claim to, but people who actually do. 97% of us today, and I was not part of, if you asked me 20 years ago, I would have said the jury is out on this problem. It isn't out anymore. The jury came back. The verdict is about as unanimous as you see in anything in science, that about 97 for us agree that we're causing the climate to warm, that it is warming, we're causing climate to warm. But if you ask people in general, not whether the climate's warming, but whether they think scientists agree the climate is warming, only 40% of them think that we agree, right? It's not illogical to say there's nothing happening, but yes, I recognize the scientists agree that something's happening. It's not entirely illogical to say that, but there's a huge gap between what we think and what they think we think, okay, if you get my drift. And that's kind of interesting, and a lot of people say it's a communications problem. I'm not so sure that's what it is. Why should we be worried about this? We're doubling the most important long-lived greenhouse gas. If we took it all away, we'd be down to 0 degrees Fahrenheit. We're doubling it. Surely that's taking a gamble, all right? And the question is, what kind of gamble is it? What are the odds, all right? It's not a binary question. Is it going to be warm, or is it going to be a catastrophe? Or not a catastrophe? Is it going to be an economic catastrophe to try to do something about it, or is it going to be nothing at all? We've got to get away from the very simple-minded binary sort of thinking about this. This is not binary. It's a probability curve. What are we actually worried about? We're not usually worried about temperature. Let me tell you, I've just come here from Boston. We've been through an absolutely brutal winter. I'd love it if it were a little warmer, okay? That's not what we're worried about. We're worried about other things. An obvious one's increasing sea level, all right? I showed you 400 feet lower at the last ice age. The IPCC is predicting on the order of 1 meter or 3 feet higher at the end of it's a fairly conservative prediction based on the history of the relationship between sea level and CO2 content. Quite a conservative measure, but a meter of sea level is on the range where there are certain places where it'll be a problem, but even in a place like New York City, it makes it much more susceptible to storm surges, even if the storms themselves don't get worse. Already, Sandy did a lot more flooding in New York because the sea level was already a foot higher along the eastern seaboard than it was in pre-industrial times. So the same storm wouldn't have caused as much damage in those days. Now, one thing that's rock solid is that hydrological extremes increase. You don't need a fancy computer model to tell you that. It's very simple physics. If I asked my graduate student to write down 3 lines of math to demonstrate that physics in a general exam and he didn't do it, he wouldn't probably pass the exam. It's very straightforward physics, okay? And what it tells us is that as the climate gets warmer, rain gets increasingly concentrated in intense but less frequent events. And what that means globally is, first of all, places that are already fairly wet, like Indonesia, get wetter. Places that are already pretty dry, like the Middle East, get drier. And in every other places, you see an increase, ironically, both of flooding events due to very heavy rain, short-lived heavy rain, and drought. And I don't need to tell you people about drought, right? You're in the middle of one here. These things have consequences. Increasing incidence of high-category hurricanes. There are quite a few of my colleagues who work on that. We use very different techniques. Is one of the things that we agree on, that the high-category events, which are rare but which dominate damage from hurricanes, become more frequent as the climate warms. And that has implications also for storm surges, and freshwater flooding goes up rather spectacularly from these events. These two things are the big killers in most hurricanes: freshwater floods and storm surges. More heat stress in all kinds of events. Now, what does this actually mean? Well, one of the organizations in our government that takes all of this very, very, very seriously is the Defense Department. Okay? These are not sandal-wearing, fruit juice-drinking hippies from the 60s. These are serious folks, okay? They're very worried about it, and they consider it to be one of the top national security threats going forward. And this is something they had to say about it. Climate change could have significant geopolitical impacts around the world, contributing to poverty, environmental degradation, weakening of fragile governments. Climate change will contribute to food and water scarcity and will increase the spread of disease and may spur or exacerbate mass migration. Now, why are they saying these things, and what are they basing it on? Well, they're basing it mostly on history. And there's a fascinating study some of you may be familiar with about the historical relationship between climate change and armed conflict and other things like that. So, for example, the French Revolution, even, of course, it had deep political roots. But if you what actually precipitated it was food scarcity. Remember Marie Antoinette saying, "Let them eat cake"? Well, that's because they didn't have any bread. They didn't have any bread because they didn't have any wheat. They didn't have any wheat because the wheat crop was destroyed the previous summer by a pair of hailstorms that went across France, all right? This is the kind of thing, this cascading thing that's attributable in this case to food. The Arab Spring, a lot of people who have analyzed that say the proximate cause. I mean, these people, right, Mubarak and Gaddafi, had been around for a long, long time. Why did it happen then? It happened then, people say, I'm not an expert, because there was skyrocketing costs of food. Why was that? Because of a Russian drought. A lot of the wheat and so forth, grain that goes into the Middle East comes from Russia. And that's why the military is worried about climate change, because it affects water and food. Those are the real risks, I would say. Now, what about the future? I'm going to close up here, and we'll get to the questions. There's a lot of tension and sort of tribalism going on in climate, which is too bad, and it's needless, and it sort of should be beneath the dignity of rational people. But the reason that it happens is because our climate models are pretty bad, all right? And this is showing a collection of a large number of models, actually fairly similar models, but run with very different parameters, predicting what would happen to global mean temperature if you doubled CO2. This is a project where actually a group in England asked for volunteers from ordinary people to volunteer their idle personal computer time for this project. So if you volunteered, they'd come in the middle of the night when you weren't using your computer and run their climate model on it, okay? And by this means, they were able to achieve much more computation than they could with a large computer. And after many, many, let's say this is 100,000 such simulations, you get kind of this bell-shaped curve. And I think this is sort of the crux of the problem if you want to look at this. Now, I've told you that temperature isn't the problem, but we'll use it as sort of a proxy for the degree of climate change. And doubling CO2, okay, the most probable outcome, as summarized by IPCC, is sort of in the range of 2 or 3 degrees. But there's a tail at the low end. It could be, 1.5 to 2 degrees. And there's a tail at the high end going out to 5 and 6 degrees. So here's the sociological problem. If it turns out to be here, we probably don't have much of a problem, frankly, okay? We don't have much of a problem because it's just not much change. If it turns out to be in this range, there'll be problems for sure, but probably we will be mostly successful in adapting to them, at least according to people who study adaptation. We'll get along, all right? It will be expensive, and there'll be dislocations. If it's out here, that really is catastrophic. No, I'm not an alarmist. I'm not Chicken Little. I'm not standing on a soapbox crying. There's a low probability, but not zero probability that we're headed for a catastrophe, okay? And everybody in my field who studied this problem recognizes it. That's the tail, okay? You have to consider the tail. You don't focus on this part of the curve. Let me give you an analogy. You probably pay $1,000 or $2,000 more for your car because it has airbags. The chance that you will be in an accident and have the airbag deploy, an accident big enough to that, is small, fortunately. But you're willing to pay more for it because the outcome is so bad. You don't want to get killed, right? We automatically, as a species, account for tail risk, except oddly enough in this problem, where we want to focus on the things that don't look so scary. We have to start thinking about the tail risk. Marty Weitzman at Harvard, an economist, has given lots of very interesting talks about this subject. But we have to be careful because doubling CO2, although it's canonical, we're on a track to do much more than doubling CO2. These are projections of greenhouse gas, of carbon dioxide concentration under different emissions scenarios. So business as usual, this curve here, we go up to about 1,000 parts per million, more than a tripling by the end of the century. Doubling is this light blue line. So under this scenario, in the lifetimes of some of the people in the audience, probably not me, we will double CO2, but we're just going to sail beyond that. Now, if we go back to the previous chart, the science really is very conservative. This is for doubling. If you go to tripling or quadrupling, you move this whole, expand this whole curve to the right. Then you're really starting to up the probabilities of very, very serious outcomes. And here's the final sort of crux of the problem is the lifetime of CO2. How long does it take CO2 to go away? Well, these are curves that show, first of all, the history of CO2 concentration, but also projections. And then hypothetically, we're going to absolutely shut down CO2 emissions when it gets to 450 or 550 or 650 parts per million, and watch what happens to the CO2. It drops at first very quickly, but then much more slowly. This is a scenario where it goes all the way up to 1,200 parts per million, which the Earth hasn't seen in about 60 million years, but which we could easily get to. And then it drops off. And look, you know, after several thousands of years, it's still very elevated. It takes a long, long time for it to go away. This is a particular climate model's rendition of what the global mean surface temperature would do under these scenarios. So the problem is, unless we can figure out how to take CO2 out of the atmosphere, we're stuck for thousands of years with the result of what we're doing now. Now, I'm going to talk I'm going to end by talking about solutions briefly. We can talk about it more in discussion. It's not absolutely my thing, but I listen to a lot of this. And I think we need to pay more attention to certain things that offer real hope. One of them is the idea of taking the carbon back out of the atmosphere. We actually know how to do that technically. We don't know how to do it very economically at the moment. We take it out, we put it in solid form, and we bury it somewhere. This is not without risk, but it can be done. And if we did it today, it would cost about $200 per ton of carbon, all right, which is an economic analysis would say is pretty bad. That's too expensive. But if it were $100 per ton, it's probably doable. So a factor of 2 sounds like a disaster to an economist, but it sounds like nothing to an engineer, right? We could perhaps engineer our way down. So $200 a ton to energy costs, it's a bit too much, but within a factor of 2. And unfortunately, there's not very much work going on. There's some going on to do that. There's not much incentivizing of people to undertake research. If we could take carbon back out of the atmosphere, there's not much downside to burning natural gas, for example. So people environmentalists like to say it's all about fossil fuels. It isn't about fossil fuels, it's about carbon. We could burn a lot of fossil fuels. Now, coal has other non-climate downsides, as you know, but gas is a lot cleaner. If we could take the carbon out, then there isn't much reason why we shouldn't do that. It's a very economical form of energy. The other thing that a lot of colleagues of mine are very interested in is in nuclear energy. This is clearly a potential solution that I feel strongly should be back on the table about this. And my environmentalist friends get very angry at me when I say this, but I'll say it again. Why is that so? Well, if you look at basically the reliability in some sense of various kinds of energy generation in the United States in green, worldwide in blue, this is the percentage of time that the source in question is online. This is 0 to 100%. Nuclear power plants can be easily, going 90% of the time. Coal-fired plants, about 70%. Hydroelectric, about 50%. Wind farms, 30%. Solar, down to 20%, and so forth. Now, I'm not saying we shouldn't do wind and solar. I'm saying we have a baseload problem until and unless we can figure out how to store energy efficiently, all right? Maybe we can. Until we can put all the solar and wind you want, but the sun doesn't shine 24 hours a day and the wind doesn't blow all the time. We need baseload, and the real issue, the serious issue among serious people is whether that baseload will be supplied by carbon-based fuels or by nuclear. That's the choice. You might get up to 30 or 40% renewables. Can we deploy it? Well, France did, okay? This is time from the 1970s to the present. This is the percentage of electricity generated by nuclear. This is the United States, Japan, France. France is 80%, and they did it in 15 years, okay? You're going to tell me that the United States can't do this, that what France did. I'm going to argue with you, okay? I'm going to argue with you. Even though I'm married to a Francophile, I will argue with you about that. And mortality by energy source. This is just the number of deaths attributed to various energy sources divided by the number of kilowatt hours produced by those sources. So deaths per kilowatt hour. Chinese coal is king, 280,000 annually, 170,000 for coal globally. And then it goes down to oil, biofuel, coal, gas. At the very end is nuclear with 90, okay? And that includes Chernobyl and Fukushima. Even wind is more dangerous. If you want to know why, we can talk about it. It's kind of interesting and bizarre. But let me wrap up now and get to the questions. The main points I wanted to get across to you tonight are that climate science, there are some aspects of climate science that are well established. No climate scientist worth his salt or her salt will tell you that we know everything. There's a lot of uncertainty, particularly in forward projections. But we do know something, okay? Projections entail uncertainty, particularly at the regional scale. No question about that. And the ill effects are mostly felt through sea level rise, weather extremes, and through indirect fallout, such as global armed conflict. The risk function is highly asymmetric. 1 degree is essentially no risk. 6 or 7 degrees is betting the whole farm, and that curve goes up very sharply in between those two limits. The rational response to risk is demonstrably being impeded by a very well-funded and highly effective marketing campaign by fossil fuel interests. This is not controversial. It's documented, okay? I'm sorry, that's happening, all right? And marketing is a very, very successful science. Rational measures probably will become possible when ordinary people begin to notice tangible climate change. And when that will happen is anyone's guess. I'll leave you with those thoughts, and I will go on and I'm going to go on and answer a few of the questions that were mailed in advance. Is that all right? Okay. So there are a lot, but I just picked a few that I thought maybe I didn't cover in my talk. What are the most material unknowns and challenges of researching them? Well, there's a long list of those. And we don't understand a lot of what's going on in the climate system, okay? We don't really understand what's happening in the Arctic very well, for example. We don't understand what's happening with hurricanes. There's a whole long laundry list. The differences that you see among different projections by climate models is one indication, one sort of quantitative measure of our ignorance of how the climate system works. There's nobody who's in climate science who will tell you that we're very confident of forward projections. Far from that making you feel better, it should make you feel worse, all right? If we could say with precision that the temperature would go up 2.5 degrees, I would say, I mean, if we had 100% confidence in that outcome, I say, we'll adapt, okay? Don't worry, we'll adapt. It's because there is a finite risk of catastrophe, and I'm not afraid to use that word, a finite but not large risk of catastrophe that we have to be worried. You know, we face this every day. If I said to you, if you let your 8-year-old toddler run across a busy highway to catch her school bus, there's a 2% chance she'll be run over, you wouldn't let her go, would you? And if I said, well, there's a 98% chance she'll make it, just let her go, you'd think I was nuts, all right? But we're pushing all our kids in front of a big school bus. I don't understand that. All right. What is your view of Henrik Svensmark's theory of cosmic ray influence on climate? Well, this is an interesting idea, not properly attributed, by the way, to Svensmark. It has a much longer history than that. That cosmic rays, which are omnipresent, but are variable in their activity levels because of variations in the magnetic field brought about by the solar wind variations, nucleate clouds. It's known from laboratory experiments of the rate at which they do that. It's a tiny effect quantitatively. It's there. It's real. It's small numerically. And the cosmic ray flux, which we've measured for several decades, is actually headed the wrong way now. It's going the wrong way in terms of explaining warmth. So that really isn't an explanation for what we've seen. There's some very good questions here, but I'll skip over to some of them. Is there any significant point that you feel the IPCC assessment reports misrepresent? What do you feel is the most important misrepresentation by the media? Well, there's a lot more misrepresentation by the media than by the IPCC, but the IPCC does not emphasize the tail risk. There's a very good psychological reason for it, and as a scientist, I'm completely guilty of this psychology. The last thing you want to be called as a practicing science is an alarmist. It's poisonous. It's a toxic thing, which is why the marketers out there use it so effectively. We're conservative. We're a little c, we're a very, very conservative bunch. We historically have under-forecast most risks. This is our mistake with Fukushima. We thought the biggest earthquake you could have off of Japan was 8.3. What they got was a 9, okay? But serious economists and serious scientists look at the whole probability distribution, and risk is the convolution of that with the outcome. It's the event probability convoluted with the outcome costs that give you the risk curve. And the tail matters a whole lot in that calculation, and you simply can't ignore it. And yes, we're going to risk being called all kinds of names by saying that tail exists, and we better darn well account for the fact that it does, even if it's in the 10% level. All right? About the media, where do I begin? Okay? The media, and I'm not criticizing them really, but you know, everyone knows that a lot of the major print media have lost their major source of revenue, which was classified ads, and ever since, because they went to Craigslist and other places, and they have been desperate for income. And no, they're supposed to make money. They're supposed to stay afloat. Well, debate sells. So, you know, if they have somebody a biologist who believes in the theory of evolution, they'll put him against a creationist who doesn't. And it's 50-50. Take your choice, right? It's a terrible, inadvertent misrepresentation of where the science stands, but it sells. And the same thing is going on in climate. Yes, you can go to that 3% club and find somebody who will stand up. I have friends who do this, and say there's no problem, all right? But they're a tiny minority, and they don't represent the consensus. And yes, the consensus is very important, okay? Nobody in their right mind, if they were sick, would do anything other than take a consensus of good doctors and not just go with the one that gives them the nicest sounding, rosiest sounding diagnosis, right? No, science doesn't advance by consensus, but anybody trying to formulate policy had better jolly well use the consensus, in my view, on anything that's important technically. So with that, I will, I guess, open it up for questions from the audience.
We have a microphone with Garrett. Pass around. There's a question right there.
I'm just going to grab it from the water here.
Thank you so much. A fabulous overview. Getting back to one of your slides where you talked that there's, it's been known for 100 years that just the troposphere effect of greenhouse gases accounts for a surface temperature between 0 and 60. And cloud cover, of course, was recognized but not really measured. Very simplistically, using your simple rule, if cloud cover were 30% of the Earth's surface, does that mean that every percent of cloud cover can actually impact surface temperature by 1 or 2 degrees? And so how do the models assume what is the cloud cover? How does that vary region by region, et cetera?
I'm glad you asked that question. So let me just start with something very basic. Clouds are interesting because they work on both the solar and infrared parts of the spectrum. So they, in some sense, both cool by reflecting sunlight to space. They have high albedo, and warm because they absorb and re-radiate infrared radiation. And to make a long story short, with very low clouds, like you have off the coast of California, it's mostly the shortwave cooling effect. And with high clouds, it's mostly the long wave effect. So this is demonstrably the most important source of uncertainty or differences among climate models is how they forecast clouds to respond to climate change. And I think the best answer that I can give you is that we don't know very much about this. We know it's important, but we don't know how to do it. All right? Yeah.
Is it a fixed input? Or
No, it's variable. It's a variable input, but if you go and look at clouds and a pretty sunset, you might notice that some of them that are doing a lot to the optics of the atmosphere are incredibly thin. So they're not even resolved by climate models. They have to be represented indirectly through something we call a parameterization. And nobody gives them a lot of weight to those parameterizations. It's a big source of uncertainty in climate models.
Yeah, we understand a lot about how carbon is emitted, how it affects the atmosphere, because a lot of dollars are spent on it. But there was a graph you showed earlier that there's an absorption or redeposition of the CO2 from the atmosphere into what? Because it cannot be another coal field magically evolving, or so is it oxidization, some process with rocks? Is it just going to the ocean? On how? I mean, everyone looks at what's happening then. No one looks at the afterlife, right? How good is that sign? That curve looked to me not like a model. It looked like some very simplistic assumption. Or is there something behind it that's so fundamental to make that kind of forecast?
Right. So the curves are based correctly. I mean, you correctly deduce that they're based on models, but there is paleo evidence for how carbon dioxide responded in the geological past to spiky events like major lava flows, for example, that put a lot of CO2 in the atmosphere. Your question is a good one, and it all depends on time scale. So if we're talking about a 100-year time scale, which is what this problem is about, is the reservoirs that are absorbing the carbon dioxide are the atmosphere and the oceans in about equal proportion. This is just based on measurements, okay? But on much longer time scales, okay, it goes into different reservoirs, and it depends on itself on the climate. So if you're in a very warm climate, you have a lot of shallow inland seas, the continents get partially flooded, you get these anaerobic environments where things die and they go to the bottom but they don't get reoxidized, and you bury carbon. That's how we got coal and oil. But also it goes into deep sea sediments, and on geological timescale it gets buried in the earth and subducted into the earth, and ultimately comes back up through the atmosphere in volcanoes. Okay, so volcanoes release CO2. The current rate of release of CO2 by volcanoes is on the order of 1% of the anthropogenic. But over millions and millions of years, they're the important source. And the biogeochemistry of the oceans and to some extent the land surface are the important sinks. It's a very interesting problem. I haven't done it justice at all.
Yeah, can you say something about the just announced AAAS What We Know initiative, of which you were a co-author, I believe?
Yes. So what the AAAS thought it was prudent to do is to draw attention to this problem of tail risk, which we don't think was conveyed adequately by the IPCC. That in addition, it's not a disagreeing with the IPCC, it's just pointing out that there's this tail, and the tail really does entail very, very serious risks to future generations, and that planning, basically trying to cope with the risk, has to acknowledge that that tail exists. That was the main purpose of that. And also to get across the point that the scientific community is largely in agreement about the basic source of risk, the fact that the planet's warming and that we're doing it. It's not controversial in science. That's what we try to do.
In your last conclusion here, slide here, the very middle point,
Yeah.
In words describes the 97% and the disparity between 41% of the American people believing that, and I think you cited Tony Lazarowitz's work. Do you have any sense, or do you know if who is studying how much money is in this well-funded campaign and where the sources are? Is that a known piece of information?
It's becoming known, and the reason it isn't exactly known now, I mean, we're talking, first of all, on the order of billions of dollars per year, something like that, is because of the fact that it's possible, in effect, to launder this money to disguise its true source. And there's a very powerful incentive to do that for obvious reasons. So there are a bunch of mostly economists who are looking at this problem, and I'm not, I've been to one or two talks, but I can't claim to be very knowledgeable about what they're doing.
Do you know who is seeking that information amongst colleagues that you've heard of at all?
Some economists I know at Harvard and Yale are seeking that information to start with, but I couldn't tell you what the whole canvas is about that. Somebody's obviously very happy about that. They're seeing it.
Could you tell us about these dangers of wind power?
Oh, yeah, the dangers of wind power. Well, the point of that slide actually was the dangers are minuscule. I mean, compared to all the other things, they're really small, but they're not zero, okay? And the talk I went to was, there's just been like a few tens of fatalities globally, and they're from all kinds of things, but most either structural failures of the windmills or things like, this happened, I think, in Canada. You get weather conditions where it rains, it's windy, the windmill's going around, the water centrifuges to the tips of the blades and then freezes, and then chunks of ice get centrifuged out. How do you like that to be in your epitaph? That's pretty weird. Yes. Yeah.
Are you aware of any human efforts to modify the weather?
Yes, I'm aware of them, at least dimly. We used to do a lot of it in this country. It's still going on. There are various private firms who will do cloud seeding for you. Whether it's effective, nobody really knows. The U.S. military did a lot of weather modifications, some of which remains classified in the Vietnam War. There was then a treaty that the U.S. is partnered to that it would never use weather modification again for military objectives. And there's a lot of weather modification going on in China, but I don't know very much about how it works, to be honest with you. Yeah. Or if it works, yeah. I don't know very much about it, but there are efforts to do mostly cloud seeding.
Well, one of the viewpoints that I've heard, and I'd be interested in your view on, is that the rise in temperature of the planet is not all bad, in the sense that crops will grow more, the higher levels of CO2 improve it, agriculture gets better, more food is available, and secondly, the rising and the changing water levels basically change things from one point to another. So there's a lot of displacement going on of activities and energies and maybe people. But it's seen by at least some communities as a more complex and not necessarily all bad. Can you comment on the balance of the goods and bads?
Sure, I can. And you're quite right to point out that there are goods, okay? There are things that actually improve as you put CO2 in the atmosphere. Certain crops grow better, assuming that you're not worried about availability of water or heat stress or anything like that. But just the carbon dioxide effect is generally positive for crops, okay? Unfortunately, also positive for weeds. So it's actually a complicated problem. But the bottom line, to answer your question, there are winners and losers geopolitically. There are places like Canada and Siberia where on the net the climate improves. What percentage of the Canadian population is within 10 miles of the U.S. border? Maybe in 100 years it will be the other way around. We'll all be hugging the border with Canada. But the bottom line point is this, and it's not made, I think, seriously enough in most conversations, is that the human species has lived through really dramatic climate changes in the ice ages, and we made it. The difference is that we're very close to maxing out, right, on the carrying capacity of the planet. We're very finely adapted to the current climate. And it doesn't even matter what that climate state is. The fact is we're adapted to it. So any change, up or down, by the way, is going to be disruptive. That's the heart of the problem. It's not that in some 1 million year time scale, this is the ideal climate for human beings, but we're just very, very finely adapted to this climate. So change is not a good thing in the net.
So I've read...
That doesn't matter to me. It's up your call. Yeah.
Yeah, I've read that there's also cooling effects from the pollution, like the aerosols you get from coal burning have an effect of cooling, and it's not actually measured very well. We don't have anything that's really monitoring it well, especially in the upper atmosphere, and that things could get a lot worse if all of a sudden we stop burning coal. What do you know about that?
That's a real effect, and it's an amazing field climate. I wish I only touched the top of the iceberg in tonight's talk. The aerosols are a strong anthropogenic influence on climate and on temperature, and they're a cooling effect. The sulfates are cooling. Black carbon is kind of a wash, but sulfates. And so one thing that happened, for example, was the Clean Air Act in the United States, Canada, and so forth, Europe, really led to a dramatic reduction of sulfate aerosols broadly in the Atlantic region. And the Atlantic temperature increased during that period much more rapidly. In fact, it had been sinking from the 50s to the 80s, probably because of the aerosols. It warmed up much more rapidly than the rest of the planet when that aerosol growth leveled out and started to go down. Now, China and to some Chinese aerosol sulfate emissions soared in the 90s in the last decade, and they've leveled out. But Indian aerosol emissions are rocketing upwards. And these are strong climate influences. The reason that I didn't talk about, I have to make choices, right, is that, and I think you alluded to this, if you stop the sulfate emissions, 2 weeks later, the sulfates are gone. They have very short lifetimes in the troposphere. And so you can turn it off fast. And that's a problem, too, because if you put a lot of sulfates and they mask warming, and then you suddenly turn them off, you get a spike in temperature. So it's a serious issue, that.
If we were not consuming carbon at all, what would be happening to our temperatures?
I'm sorry, to what was the last
To
one?
our environment.
If we weren't consuming carbon.
Yeah, if
Yeah.
there were no people consuming carbon at all, what would happen?
So I'm just trying to understand the question. Are you asking what would the climate do on its own if we weren't changing?
Right.
Is that the question? Right. Okay. So what we would be doing, we think, is very slowly declining into the next glacial cycle, which would commence in order 20,000 years. And this is from Milankovitch foresighting. On top of which you have the normal chaotic variability of climate and so forth. If you're really a futurist and you don't think on the 100-year time scale, but on the 30,000-year time scale, we should be storing carbon somewhere on the planet because we're going to need it in 20,000 years. No, seriously. If we want to think really on those timescales, that's one strategy for doing it. But the immediate global warming problem is occurring on a much shorter time scale than these long cycles. Now, aside from that, there's so much I haven't talked about. It's very frustrating. There are volcanoes, and not just the ordinary, big volcanic eruption like Tambora or Pinatubo, which cools the climate for 2 or 3 years. But you have, in the distant geological past, these big flood basalts, which seem to coincide with mass extinctions. And one of the routes you get from a flood basalt event to a mass extinction is through climate change, either through CO2 or just aerosols that you're putting into the atmosphere. And that's a very active field of research, but that's on a much, much longer time scale. So you can't predict the volcanoes. You can predict the Milankovitch cycles. That's why I say, from what we know, we're in a 30,000-year cooling period.
Can I ask you to say a little bit more about the physical causes of what would cause the tail that you're saying is what you think is the big thing not given enough attention? So the reason I have that question is you showed the charts for what the satellites have measured for the lower atmosphere, and since they started, CO2 has gone up, say, 25%, so that's the third root of 2. So they measured the difference of, on your slides, like 0.35 degrees C in that, or 0.3 in that amount of time. So if we tripled that, that would be on the low end of that scale. So I'm just wondering, what are the physical mechanisms like additional moisture in the atmosphere that would expand that so much? And what are the measurements that we have? What's the evidence that we have about whether there is that additional water vapor?
Okay, so I think it's a very good question. If we double CO2 and we don't allow any feedbacks, we don't allow the water vapor content of the atmosphere to change, we don't allow ice to melt, all kinds of things, that would give us about a 1 degree warming of the planet. Most of the difference between the 1 degree and the projections of 2.5 or 3 degrees is water vapor feedback. And what we observe when we look at natural climate variability in nature, when we look at models, is that to a first approximation, the relative humidity of the atmosphere is invariant, which means that the percentage of the saturation vapor pressure is sort of the same. But the saturation vapor pressure goes up exponentially with temperature. So there is no model that shows a negative water vapor feedback. It's just a question of how positive. It's not terribly uncertain, that one. The uncertainties come mostly through clouds and to some extent through sea ice. You know, if the sea ice melts, and it is, you replace a white surface with a black surface. You absorb a lot more sunlight. You get more heating. Clouds can work either way, and it depends on what happens. So the scatter in that diagram is, a lot of it is clouds.
We have one more question?
We can't explain past climate change without those positive feedbacks, by the way. I mean, it's hard to do that.
Just, I've heard that as the climate warms, that there would be methane gas released from the
Clathrates, yeah.
And were the projections that you were talking about taking that into account at all?
They weren't. And, you know, for a while we thought that might be important, and we don't really think it's so important anymore. But it's true what you say. So what he's referring to is that methane is a very powerful greenhouse gas, but there isn't very much of it in the atmosphere. A lot of methane is locked up in sort of solid form in continental shelves and deposits. And if you reduce the pressure on them, or if you warm the seawater, those can potentially be released. Also from tundra, methane is locked up in tundra. And in recent years, we've actually gotten a much better handle on the net reservoir of methane that's out there, and we don't think that it's going to be accessed by global warming. So that range that I showed you, that bell curve, didn't have any of that methane feedback. Yeah.
Okay. Thank you, Professor Emanuel.
Thank you. I can hang around and talk to people if you want. So thanks.
So Carrie will be available after this next bit. Doug Sprang, who runs this program, is going to talk to us about future events, and then you can talk to Carrie one-on-one, okay?
Ask him to stay for just a minute.
Yeah, if you wouldn't mind staying.
Okay, hope you don't have too many.
No, I'm in.
Thank you. Real quickly, a couple of announcements and our usual thank yous. I will say, too, you're going to be able to stay for a little while to maybe answer a few one-on-one questions. So if you didn't get your question asked, come on up afterwards. This is a very significant thing here I want to tell you about. It's fairly new, being done by primarily out of the MIT Sloan School. It's called the Climate CoLab, and they're doing crowdsourcing. And the purpose of it is to generate ideas for addressing global warming problems, and also to gain support for these ideas. And the way that they do it is they have these contests in 18 different topical areas to optimize the creativity of solutions. So it's not just a few, but it's like 18 different topics. And you can submit your ideas either as individuals or teams. And there's expert review. So the people that actually review the proposals are experts in their field. So it's not a casual selection. And finally, the winners get to present to global policymakers. And that means that they can really influence people that could actually do something. So if you're interested in following up on this, on your program, the website's on your program. It's the climatecolab.org site. Please follow up and take a look, because I think many of you who are interested in this subject may really like to get involved. Okay, coming attractions. Well, I just have to mention that we sold out the National Ignition Facility in under 6 hours from the time we posted it. And it's so popular that we're going to do it again and again. So, but it takes time, because these guys are not open all the time. It's a national lab, and they have a lot of security issues and so on. But that's coming up on April 16th. We hope to do at least another one in the summer. Very popular tour we've had twice now before is the tour of the California Independent Service Operator, or ISO. These are the people that manage the flow of electricity all around the state in the large quantities, and they have a tremendous tour and visual experience on how they actually do this. And for those of you who are interested in how this all happens and haven't yet done this tour, I think it's a must-do. It's really, really educational. And finally, we're thinking ahead, and fortunately, I think Professor Emanuel here helped us out a little bit. We've already got an agreement from Professor Dan Sitso, that's how he pronounces it, to come and talk about how the atmosphere affects climate change. And for those of you who know, and have seen a little bit written about him, he's an expert in clouds. So clouds are a really important part of all this, and if you really enjoyed tonight and all the information that you got, we're going to do it again in about 3 months, and it'll be deeper, kind of look at some of these things, but along the same lines. Because I think understanding how all this works and understanding the facts of the matter and everything from people who really know, that do the research, is really valuable when you start talking to people that have been influenced more by other sources. So the first thing we do always is to thank you for this, and it's a, where is it? Okay, great. It's a, we'll go ahead and present them. So, and this is a special one. It's a bottle of Caymus Cabernet, and those of you who know that the Caymus is a very good label. But this is a little more than this. This is, came out of my private collection. This is 2007. The only thing you can buy today is 2011, and you probably put it on the shelf for 5 years. But Carrie, you can actually drink this tomorrow if you like.
I'm very tempted. I'm tempted to drink it now.
We'd like to thank Park for providing us with this wonderful facility. Scott Elrod's our professional host. He's assisted by Sean Garner. I don't know, Sean, are you here? Sean? No, he's not. Oh, but Rob's here. Rob McHenry. Unfortunately, I didn't know about you coming. I didn't get it on the slide. But Amy Hommans, the administrative support person that we have, and she helps us nail this down and schedule the security and everything. Marcy Steiner is our caterer. And if you like the food, we have a new menu tonight. Give Marcy a hand. And always with us is Joe Sullivan in the AV booth, and Hank Magnuski, who normally does the video recording of our events here, couldn't make it tonight, so Joe has actually done the recording. We will post this video on our website in a couple places. So for those of your friends who didn't get a chance to be here and want to see it, it'll be there in entirety, including the Q&A. Park is doing a number of things, and you can read this faster than I can say it. But in 3 words, I guess it's companies looking for sponsored research, startups that want to be incubated, or if you just want to work here. It's a wonderful facility, and just, get on www.park.com and you can find all this stuff. Finally, I want to thank all of the MIT Club of Northern California volunteers that make this possible. Greg, our event manager, stand up and take a bow. Greg will be doing Professor Sitso as well, so he'll be back. And then the other folks that are all mentioned here that welcomed you or poured your wine or whatever. I hope to see many of you back on June 25th for the how the atmosphere affects climate change. And we're going to just probably just do tours in April and May, but we have 4 of them actually planned, 2 of them only scheduled at the moment, and there'll be more, and you'll hear about that. We'll send you the emails announcing them. When you come to an event here, even if you're not an MIT alum, you get put on that distribution list and you find out about what we're doing. So, and we welcome you all and wish you all a safe ride home. Thank you, Jim.
Grab my laser pointer.
I'm going to let them get